Okay. Well, let's keep our fingers crossed that Alyssa decides to present. Maybe she's just caught in traffic or something.
Hmm. I would believe it's sensitive, but you'll be in the back of the right? No, but I'm still feeling out. You want to go? Well, I think his office hours today, the professor is at 4 to 5. Oh. But I'm passing 4 to 5, and they're like, no. I mean, yeah, quiz though. That's what I'm saying, if he gives the quiz in the beginning, not even let us leave. Here's something. Oh my gosh.
We're just waiting for Alyssa.
Oh, dude. There's no sense in it. They're making it. It's not, huh? Not too much now. Mm. What's that? I think this one's.
Yeah.
Remember the vocals? I think we'll go aboard one day. How do you remember that something?
What?
It's like telling you about. There was a time out hours of that. From the board.
Hmm.
About what happens. You can like you were done. You sound good.
Yeah, I'm not sure what the question is here. Are you saying how does my memory work?
Yeah.
So I don't leave space for students' names, and instead I remember really obscure things about maps. Does that help?
Okay.
Like geography, like city streets. Like if you drop me in San Francisco in a random place, I'll know how to get from point A to point B. Yeah. Brains all work very differently, right? So especially when you see something a bunch of times, you start to see the patterns for it. It works. Okay, we'll wait another 2 minutes and then we'll start without Alyssa. Is someone else here in the chat on the onlines? Okay. That's perfectly okay. Sometimes we get held up, you know? Oh, should we all hide and pretend like we're not here? Pranker. That's funny.
Run to the right person, that's nice.
Oh, sorry.
Hmm. You say you choose to not remember students' names as if our department's big or something.
I don't say I choose not to. I say my brain does not. No. What?
Is it like naturally?
Yeah. Like I meet someone at a party or I meet someone on the street and they introduce themselves and it's gone. And then it's my cousin or something, or like today in fluids, like Zori's name just like completely passed me by. And I was like, what the fuck is right? Sometimes you just remember certain things and sometimes you don't.
That's crazy. Mm-hmm. You're over. Not very crazy. Watch, I have the. Yes, so as yeah, wait till we come back. After Santa Barbara, it's gonna say 25. If we turn it on lot, like, pending each one. I'll just save it on my log. We'll like it. And if we make it ready for. Yeah, on this day. Like subtract. And then we can compare, we'll call it, that's great. Just like. The website you use for 33. That'll be the difference. The area will be different. Some people don't. Nice. Oh, nice. You're touching that. Yeah, that is it. 1/3. One certified and one. I'll give it. You can both be. Yeah, that's great. It's like a whole ad mix. And it makes it easy, everything two different changes. Does everything work? They have the same. Therefore, we can compare it. Yeah. So yeah, that. I'll prefer to. Yeah, because we are big one. Yeah, it's free. Because you know, people do big red lights. That's not normal. Did anything change from the picture I took of yours? Yeah. Still not.
Okay. Okay. Do you want to present from here? Or do you want to present from? Okay. So you'll just zoom on and then I'll share your screen or vice versa. Because I can just have the slides open or the book open. You have an example today for choosing errors? Okay. So then I can just have the textbook open and you can have me go up and down. Okay.
22, Marathon principles. This one essentially is describing how there's every number error one dimension method has errors from approximately to the solution. These errors are expressed in terms of the step size of variable h. And from our main source of error, it's called the approximation error, where from both the trapezoidal and the Simpson law. And that is from calculating the error under the approximation. Wait, on page. That was essentially what that first two paragraphs were saying, and then now it's going into the trapezoidal function from equation 5.3, where they have that whole variable, but now it's going into 5.11, where they're taking the positions where we evaluate the intragram of f of x, which is our example point. And then we're substituting for the values of xk, which is represented as a plus a h. And then we're just substituting that in using the Taylor expansion for f of x. That's good. Like the next page. On the top section, this is where we get our approximation error. Also, it comes from the trapezoidal rule. So they do the whole Taylor expansion with substituting with the variables from the trapezoidal rule equation, and then we're left with the sum of equation 5.16, where the first sum on the right hand side, the summation essentially of f of the function of f, considering xk minus 1 plus the function of x plus 1, that first function there is the summation in the trapezoidal rule. It's pretty much the same when we're finding the f of a s, plus the f of b back in the trapezoidal equation. And then on the second term, but now this is only evaluating from the sum of xk minus 1 and xk, where this tells us about the amount we need to add to the rule from our trapezoidal equation. The second term with the term h squared, this is only evaluating at points A and B from our first derivative. And then our third term, h goes to the cube, is an overall constant. This is the trapezoidal approximation of the second derivative from A to B, where we're looking into, then they continue on by looking at this constant, leading into another substitution. Instead of our left-hand side being f of x, now they're going into the second derivative of f of x, a function, on the left-hand side. And then once they do those substitutions and canceling out some terms, we are left with the approximation error of the H151 equation 520. And this is essentially the Euler vacuum.
Euler Maclaurin, yeah. So this is just like the car, McLaren.
Formula. This continues into the next power term. Only even powers in this equation survive. All the odd powers of h are canceled out essentially from this. And this is just telling us if our h is small, then we can neglect the higher terms of h to the power of 4 and so forth.
Right. So that's something we kind of saw before in integration, or sorry, in doing the derivatives. We're just seeing it again here. Okay.
They were talking about the first integration rule, first order integration rule, and this is coming from equation 519. This term's proportional to the h, and it's leading to an approximation error of h squared. This is accurate to OH, and it's an error of the factor of OH squared. I had to look up what essentially that constant O is.
So that's not a constant, right?
No, it describes the quantity on how it grows or like shrinks in the step size of each.
Right. So this is a way that we talk in mathematics, we say of order. So sometimes you're familiar with something like significant figures. They say, give me an answer to two significant figures, right? Well, we do the same thing, except we think of them in powers. So for example, if you have a term that is, let's say x cubed, and x is 1,000, then x cubed is certainly the largest. In terms of x squared, in terms of x, probably not as important as the x cubed ones, right? Similarly, if h is smaller than 1, then the smaller numbers are going to be less important than the bigger ones. So you have first order, second order, third order, and each of those represents a level of confidence. To the 0th order, that would be like an average. To the first order, you're taking the primary effects, second order effects, right? Each one as you go down represents more and more nuance in the work that you're doing, right? So here, it says first order 0h, right? It's accurate to h.
Like the error increases proportional to age.
Mm-hmm.
Or whatever the guard is.
Mm-hmm. Good. Okay, do you want to talk about the rounding error or you? Yeah, okay.
Times the value of C is just an error constant. Makes those to the tens to the power of the -16. And then with equation 20, the approximate error gets smaller as h gets smaller. And then that leads to more accuracy with a larger number of n of slices. And when n is not inclusive of about 10 to the power of 8, the rounding error is important, which reaches the maximum accuracy for a computer to evaluate. But this is like an unusual size of slices, so it's safe to assume to ignore the rounding error.
Right. What did we do? So on Monday, how many slices do we end up taking? Like we started with like 10 slices, 10, 100, 1,000. So that would be 10 to the 1, and then 10 to the 2, and then 10 to the 3, right? And how long did it take us to do 10 to the 3? You remember the time? It took longer, right? Than 10 to the
9 times.
took 9 times longer than 10 to the 1. So 10 to the 8 slices, right? That's a lot of slices. That's enough slices, some would say, right? Okay.
So then the next one was the Simpson rule error. This was from equation before.
Mm-hmm.
Where age a small error. This is less of an error than the trapezoidal rule. Or rounding error equation, it's
Yeah, I'm just gonna balk you off for a second here. So I just want, the details aren't important, but the thing that matters here is the order of the error for trapezoidal was h squared, and the order of the error for Simpsons is h to the 4th. So for the same size h, you already get an improvement just because the approximation itself is better, right? Okay, now you can talk about it. Yeah.
they stated for their slices was 10,000 to the maximum accuracy for a computer. But essentially that's it. Still kind of like where they said it's only to use like a couple thousands for n, then you'll receive a great accuracy because the computer will reach its precision. For 5.21, the practical estimation of errors, this is going back to Euler's formula, which is similar to the Simpson's rule. This is calculating an error by doing the steps of by evaluating from x equals a to x equals b. you have the same row of steps that we've been doing, and you have step size, H equals B minus A, number of slices, number of steps. And then essentially you double your steps. So now you have B minus A over the double amount of number of steps you took. And that's essentially just half of your first step size. And then go to the true values of the interval minus
Minus what?
now they're doing this, they're forming an equation where their true value of the integral, and then their first estimate integral, and they're taking the difference of this, and this is the error essentially of that h squared. And then they're relating it back to that difference where for a true value of interval equals the first estimate plus the h squared, your error. And then they did it again by doubling the first steps, and that's essentially just the same order, but now you just have double steps.
Yep.
And for 5.3 is choosing the number of steps you have. This was just essentially finding the appropriate number of step size, steps n or the step size 8. Where you have more steps, you have a smaller error, but it takes more time and calculation will be a bit slower for that. Then they're talking about how you could trial run with different number of n to see how the result changes. So you start with a value n, and then you double your n value, and then you compare it. And if the change is smaller, then you can stop. Or if doubling, or you keep doubling until you achieve the required accuracy.
Now, some of you are going to really want to go with a factor 10 there. Resist that urge. Factor 10 gets bigger much faster than factor 2, obviously. Yeah, question?
5.2, 5.28 is the new error that was recently method the integrals, and I2 is trapezoidal rule and I1 is trapezoidal rule, like doubling n. And that is different than the Orban-Claren formula. Is there a name for that second formula that we're going to use for besides 5.6? Like there's the first formula for that error, which is the Orban-Claren, the derivatives, and the 1/9 for the Simpson rule. And then there's this new formula, 5.28, which is 1/3 I guess it's, I don't remember if that's for Simpson or not, but it's like 1/3 I2 minus I1. I'm going to use the one, there's a trapezoid rule in exercise 5.6. Is there a name for this other method?
When I was reading, I was just good at something from Simpson. That's just another error. That was
Yeah, what we're thinking about, just for folks who are following along at home, is this one, and we're just imagining what is this compared to this approximation that we had earlier, where you had this coming from the derivatives themselves, right? And this is the Euler-Maclaurin one. This comes from using the Taylor expansion. Really, it's a Maclaurin expansion, but no one says that. And this one here, epsilon 1/12 h squared, blah, blah, blah. But if you go ahead and you look here, this essentially takes the integral when evaluated at 2 different times, that is to say 2 different h sizes, and says, how close are they? So this really is, let's see, this uses like successive approximation of the error, so to speak, right? Because this is an approximation I1, and this is a better approximation I2. And how close they are is also a valid metric of your error. So the idea that error is identical in every way of thinking about it is wrong, right? Because our ability to understand how well we approximate something, right? So for example, we start with the function, we do the Taylor expansion. Now the Taylor expansion is correct if you take all of the terms, but it's not if you cut it off anywhere. That's an approximation, right? Similarly, this is an approximation. And so those two errors should be similar, but are not required to be the same. You see? There are two ways of showing what your error might be. Yeah.
Fine with x1, x2, and x1 with the two steps, I think.
Yes. Yeah.
That's the one that we choose, so there was x2 and there was error, we used the error to.
Right. Yeah. Because we would compare the two of them, right?
Which, even though we have the error for I2 and I1, which is the control? Is it the 2n window or is it the n window? But we store the actual.
Between these two?
Yes.
Your choice. I mean, let's say you're reporting this to your colleagues, right? And you're saying, I did this integral and here's the accuracy on it. You could say I1 plus minus epsilon. And I1 plus minus epsilon is necessarily should include I2, right? It has to. Okay. Cool. Keep going, Alyssa. Or are you done? Do we do Romberg integration in this one?
Then continue on talking about the figure on the left side, where you're talking about it's the locations of the sample point. They're regular space down, from the troubles areas and troubles are on both sides. So, the lower line depicts when you double the number of slices, this adds an additional set of sample points. And from following their process, they choose the initial number of steps and one, they doubled the number of steps, they calculated the error. And then the error was less, if the error is less than your error received, then you stop. If not, you repeat number two and then keep going with the process. The same goes, it's similar use for those Simpsons rule, where you choose the initial step of your target accuracy, you calculate the stems. Then at your initial value interval, you double the number of steps using the equations from 5.37. That's on the next page.
The next one on 148? Or the one before?
Fine.
This one. Oh, this one here.
There's doing process. But now for the solution of the method, you do the same thing. You pick your initial values and you double the number of steps you have, and you calculate your new values and your new estimate, and it will also calculate your error. And if your magnitude error is less than the target accuracy you wanted, then you stop the interval or you repeat the process again. Right, double.
Cool. How do folks feel about this? Any questions for Alyssa? All right. Okay, so let's do some of these problems, particularly when we're thinking about error on Simpson's rule. I believe I assigned 5.5 and 5.6 for today. Let's see what I chose. No. Hash dollars. There we are. Oh wait, no, this is math. Is it math? Hold on. Yeah. We're gonna do 5.6, not 5.5. I'm bad at reading. Oops. Okay, so let's break up into what groups we did on Monday. Did we finish 5.2, everyone? And we're not done? Okay, so you're gonna finish 5.2 and then we'll do 5.6. You guys done, ready for 5.6? Okay, so when you're working on the problem, right? You're going to modify an earlier one. I would recommend modifying something that you know works. Okay. And you're going to use the trapezoidal rule with 20 slices. N equals 20. Okay. But also create an estimate of the error using this one. Okay. Once with 10 slices, once with 20. Okay. And then compare this to the true value 4.4 and the uncertainty on the error, which is kind of what we were just alluding to, between equations 5.28 and equation 5.20. Right? This is the Maclaurin formula. And of course, you can take the derivative of f, because I gave you f, and that's a polynomial, and we know how to do that, and evaluate it at the endpoints. So you can start off before you even do a single calculation by finding out what you're supposed to get. Right? And then compare it to what you do get. Chinchillin? Okay. We might have time to do 5.7a. Oh, you didn't make time? Are you alone?
Oh, yeah.